All right, so here I just want you to take a look at these colors, because one of the things that's really interesting about the transition metals is the fact that they're the ones that form all of these cool colored compounds. And so today we're going to talk about the colors that we see with these transition metal complex ions, and we'll mention a little bit about the fact that they notice that it has some properties, like some of these are attracted to a magnetic field, and some of these ions are repelled by a magnetic field. And so we're going to talk about a theory today that tries to explain why we see these colors and why we see these magnetic properties. So in order to do that, let me find this. Nope. That's what I need. We got to go back to our d orbitals for a moment. So I just need those pictures, but we're going to talk about something today that has a coordination number of 6. And if it has a coordination number of 6, that means it's what shape? Octahedral. Okay, so we're looking at something that is octahedral. And I'm going to use an example like iron 2+. And I want you to notice right away this does not follow our rule of thumb, because that's only a generality of doubling that charge. But this one can form octahedral complexes and have a coordination number of 6. And if we were to think about the orbital diagram for iron 2+, and of course iron 2+ ends at 4s2, 3p6. So we've got all those. I'm just going to start with the 3s. So like we have our 3s electrons, and I'm going to write these in order of increasing energy. So then we have our 3p electrons. And then our 4s electrons. And then our 3d electrons. Because it's 3d6. Now, if we're talking about iron 2+, and we are, which electrons does it lose? The 4s. So these are gone, right? Our focus today is going to be on these 3d orbitals. Those are the ones we're going to really look at, because that's the one that this theory is going to apply to. And the theory that we're going to be talking about today is known as crystal field splitting. So crystal field splitting, and I'll get into what that actually means. But in order to understand that, we need to look at these pictures of the d orbitals that I have here on the left. And if you look at the axes on these, if we look at this top picture right here, the axes are actually located in an octahedral shape. You could kind of think of those as, you know, the equatorial and the axial. So if we look at a ligand coming in, I'm just going to call it L. If a ligand comes in to bond, we would have ligands coming in the axial positions. What does a ligand contribute to the central metal cation?
Electron pair.
An electron pair. So it comes in with its electron pair. Rebecca, I'm getting really hungry.
Me too, we shall.
Yeah, we're getting distracted, and now, you know, I can't focus anymore. Stop. Milan. Not. Okay. See, look, you see, I lost my train of thoughts, just because now I'm hungry.
It'd be more like, I want to learn. Industry. Yeah.
Nobody has, anyway, no Cheetos today? No Cheetos today, okay. All right, back to this. So the ligand comes in and it's bringing an electron pair to that central metal cation. But think about what that d orbital means. The d orbital means that inside of, you know, these lobes here, this is where we're going to find an electron. Well, when an electron pair comes in where there's other electrons, what happens? They repel. So the fact that this ligand is coming in and bringing an electron pair right here to where there is a lobe of that orbital, there's some repulsion. And same thing with this ligand coming in the other axial position, there's some repulsion. And then we have the ligands coming in the equatorial positions, and I don't know why I put F, that's weird. And there's also some repulsion in that little donut-shaped spot as well. Not nearly as much, but still a little bit of repulsion. Okay, let's compare it to the next one below it. If I think of the ligands here, if I put a ligand coming in the axial position and a ligand coming in the other axial position, notice in this diagram, it doesn't bump directly into a lobe anymore, right? But when I look at the ligands coming in the equatorial positions, does it bump into a lobe? Yeah, and again, there's some repulsion. And so both of these orbitals experience some good repulsion when the ligand comes in. All right, let's look at this top right one. When the ligand comes in, bless you, do any of these ligands bump directly into a lobe? No. So there's not as much repulsion here. What about the one right below it? Do any of these ligands bump into a lobe? Not directly, so there isn't as much repulsion. And the same is true of the last one. None of these bump directly into a lobe. They kind of go in between the lobes. So the idea here is that when the ligand has to overcome repulsion, and that d orbital is experiencing repulsion, the d orbital actually has now increases in energy. So here's what happens. Normally, the d orbitals, we would consider them to be all at the same energy. So these are the 3d for iron. But when the ligand comes in, what happens is that those d orbitals actually split in energy. So here's energy. And the ones that become higher in energy are those two that experience more repulsion. So that's dz squared and dx squared minus y squared. I don't care that you know the labels of those. But if I scroll back up here and I look, here's my dz squared, which is one of the ones with repulsion, and the other one I circled, dx squared minus y squared, is the other one that has repulsion. And so those end up at a little higher energy. And then the other ones, dxy, dyz, dxz, are still at a lower energy. And it has everything to do with the ligands coming in and feeling a repulsion. This splitting, this difference in energy here is designated delta naught, and that is literally called the crystal field splitting. It's an energy. And so there's an energy difference within those d orbitals. Now, that being said, there are actually two ways. I mean, the size of the crystal field splitting actually will depend on what ligand attaches, because it could split just a little bit, or it could split a lot. And you could have a very large crystal field splitting energy. So what really causes it to have a difference in crystal field splitting is the ligand. So I'm going to put a little list of ligands as which ones kind of influence big splitting or little splitting. The ones that don't split it much, they must not have as much repulsion, are primarily the halogens and hydroxide. So I'm going to put this list in order, but you do not need to memorize them in order. You just need to know generalizations like, wow, all of these on this end are halogens or hydroxide. And so this group here tends to cause just a little split in energy. And then if we keep going, I hit water and ammonia and ethylene diamine and nitrite and cyanide. And down at the other end here, these tend to cause a much larger There's a bigger repulsion factor going on, and so the field splits more and causes a bigger difference in energy. The ones that are the halogens at this end, these are called weak field ligands. They don't cause as much of an electrostatic attraction, and so the field doesn't get split as much. And, oh, I should put crystal field splitting up here. Sorry, just put crystal splitting. And so these are weak field ligands because they only cause a weak difference in the field. Over here, these are strong field ligands. They cause a big split in the crystal field. So now the question starts to become, well, what does that matter? Why is that important? And here's how it explains two of the things that we're looking at today, the magnetism and the color. We're going to start with the magnetism, just kind of make a sweeping generalization here. But taking a look first at this small split, iron has 6 electrons. The difference in the d orbitals is not great, and so it continues to follow Hund's rule, where you fill every orbital once before you fill any twice.
Does it matter which one you fill twice?
It'll be one of the bottom ones. It should typically be the first bottom one, whichever one. I don't care that you label the d orbitals. Here's the difference. Eventually, when this crystal field splitting becomes too high, it isn't able to do that. So when it comes and tries to fill all the electrons once, it actually is not able to come up and fill that top one because there's too big of a difference in energy. So it ends up just filling these twice on the bottom. This difference in the fact that in one case we have a lot of unpaired electrons, or unpaired spins is what they actually refer to them if you think about quantum numbers and the spin, leads this to be paramagnetic. With paramagnetic compounds have a lot of unpaired spins. A lot of unpaired electrons, and what that causes is it actually causes them to be attracted to a magnetic field. And so they notice that in some cases, like iron, for example, is attracted to a magnetic field, but only when it has certain ligands attached, like the halogens, for example. On the flip side, over here, when we've got lots of paired spins, or a lot of paired electrons, this is known as diamagnetic. And so it has mostly paired spins. And this is repelled by a magnetic field. And certain ligands will cause that same iron to actually be repelled by a magnetic field. And the reason is because it splits those d orbitals much, much more so that the electrons can't spread out. All right, another vocabulary term. You can maybe explain to me why this is. But in this particular case, this is known as high spin, versus this case is known as low spin. Why do you think this first one is called high spin? Why is it called high spin? What do you think, Danny?
Because you have electrons in the higher level spinning, and you don't have low spin.
That's good, actually. I like it. It's not probably the reason behind it, but it is a good observation to make in a high spin complex. That in a high spin complex, you do tend to have some of them in the higher d orbitals. What do you think, Lydia?
Does it have to do with like the electrons moving faster in the high spin than in the low spin? Because when you do with like the pair electrons
Good guess. They actually still tend to seem to move just very similar speeds regardless, but it was a good try. Turns out that high spin is simply referring to high numbers of unpaired electrons or high numbers of parallel spins. Parallel meaning, of course, the arrows are going in the same direction, which means they're spinning in the same way. So high spin, this first case, has a large number of unpaired electrons. And so this is the high spin complex versus over here, this is the low spin complex. We don't have any, or we would have very few unpaired electrons. And so this can be handy like when you're working through blues problems, for example. It might not tell you that there was a big split or a little split, but it might say in the high spin complex, well, as soon as you see high spin, that means that it's able to spread out a lot. If it's able to spread out a lot, what's true about the energy split? It's low. So being given that information can be helpful as you work through problems. All right, so let's talk about color for a moment. When we go back and look at these, the first question we have to analyze is, why are they the color that they are? So let's think physics for a moment. If something appears green, why does it look green? Killian? Okay, so if you shine white light at it, it will, one way that it could look green is it will absorb everything except green. Green will bounce back to your eyes and you will see green, right? Well, oops, in these solutions, if we shine white light at them, they are in fact absorbing some wavelengths and allowing other wavelengths to pass through to your eye. But it actually is working a little bit opposite. If this is a green solution, it isn't that it's absorbing every single thing except green. How else could it look green? What? Well, it could be blue and yellow. So maybe it's a combination of things. But let me scroll down here to this color wheel. You have a color wheel in your book. Did you see that in the chapter?
Yeah.
Seriously? Like you have not? What are you doing? You guys saw the little color wheel? It didn't look like this, but it was like a color?
I said yeah.
One person? Wow. Test is Monday, people. Test is Monday. Okay, this is a very simplified color wheel. I chose this. The one in your book is actually has more colors on it, but I wanted to stick simple just for this discussion. But here's the idea. This is a color wheel that shows complementary colors. And it turns out the reason when all of these colors are present in white light, what makes it appear white is the fact that all of the complementary colors cancel each other out. And so, when I look at, this isn't true white light, but if I look at true white light, I don't see a color to it because the blue in the white light, because there's blue in there, gets canceled out by the red or the orange. These cancel each other out, so I don't see a color. And the yellow cancels out the purple. And the red cancels out the green. And so when you put them all together, we don't see any of those individual colors. We see white. But what happens is, if I have white light, but I remove one of the colors, if I remove, say, purple in my white light, what will I see? Yellow. Why? Because the red and the green still cancel each other out. And the blue and the orange still cancel each other out. But what doesn't get canceled? Yellow. And so that's the idea here, that another way, for example, back here, if this appears green, one way is it could absorb everything and reflect green. What's another way that could appear green? If something in here absorbs red, then what I'm going to see with my eyes is green. Because everything else will get canceled out, but green won't because its complementary color is now gone, and it will appear green. So if we go back to what we were just talking about then, let's make that smaller. Let's figure out how that plays a role here. I'm going to look at the low spin complex for a moment for iron. So here's my iron. We're talking about the low spin, so it's going to, you know, have a larger crystal field splitting here. But what happens is if you shine, you know, white light at it, at your complex of iron, you know, the light has a large number of different energies associated with the different wavelengths that are found in that. Well, if one of those energies corresponds to the crystal field splitting energy, what can happen is that one of these electrons could absorb that energy and bump up, absorb that energy and get kicked up to the higher d orbital. Now, as it absorbs that energy, we know that energy is Planck's constant times frequency. We know that frequency times wavelength is equal to the speed of light. And so let's say, you know, that energy gives us a frequency. Of course, with that frequency, we can calculate a wavelength of light. If that wavelength of light, let's say, corresponds to an orange wavelength, I don't know, I'm just making one up, will my solution be orange? No. This would represent the wavelength that it would be absorbing, because that would correspond to that energy. So if it's absorbing orange, what color would we see? Blue, because blue is the complementary color. Now, if you think back, remember when I did the demo where I just took the copper chloride and it was basically the copper with the water molecules around it, and it was that light blue, and then I added ammonia to it and it turned into that really deep, like royal blue color?
Yeah.
Nod at me, thank you. Okay. So why did that happen? Well, you know, if we think back and we look at this and we look at our ligand, well, here's water, here's ammonia. Ammonia creates a stronger field, a crystal field splitting. So it's going to correspond to a bigger energy. Well, that bigger energy is going to correspond to a bigger frequency, smaller wavelength. It's going to shift that color to a little bit, what it's absorbing, to a slightly smaller wavelength, which is going to shift the color we perceive somewhat. Now, it still was blue. I mean, it didn't change it from like blue to yellow. And that's a matter of how much difference the field gets split. And certainly water and ammonia are very close in terms of how much they split. It's not like we changed from cyanide from iodide. That would be a much bigger difference. We might see literally an entire color change where it's blue to yellow. But in that case, we just shifted it a little bit. Questions on that, Rebecca?
Could you move an electron up and then have an empty?
You could. You could. So either one of these could absorb energy and then correspondingly get a color, as long as you have an electron down here and openings up here. So there are going to be cases where, you know, if you have, for example, zinc. Zinc is in many cases not defined to be a transition metal at all. Because one of the things that defines a transition metal is to have not completely filled d orbitals. And zinc and cadmium and mercury have completely filled d orbitals. So many scientists will say those are not transition metals at all. But, you know, zinc is completely filled. There are nowhere for electrons to move. So it's not going to be able to absorb electrons and therefore have a color associated with it. So not everyone is going to have that option. It has to have space to do that. And then, of course, you know, because we can still have some weak field ligands here, and that will contribute to a small energy, which would be a small frequency, which would be a big wavelength. And so that can definitely happen. Okay? All right, what I'm going to do then is I'm going to actually stop here. And the last couple minutes of class, I am going to give you an equilibrium problem to try. Unless you want it now. You want to do it now and then work on problems? You want to work on problems and do it now? Or and then work on problems?
Do it now.
You want to do the equilibrium one now?
Yeah.
All right, let's try that. All right, let me pull it up here. All right, this is separate though. We're done with the colors. This is just kind of carrying us back because I wanted to give you a tougher problem. So up here is this problem. So I'm going to go ahead and why don't you take the next, I don't know, 5 minutes or so and see how you do with it, and then we'll go over it. And then the rest of the time will be for you to just work on the blues. So go ahead and try that right now. So let's talk this through and see how you did on here. So as we're looking at this, you know, first of all, you establish that this is an equilibrium problem. And so you can write an equation here in terms of the fact that, you know, we've got this Kf value, so we've got the metal ion, the ligands. You can write an equilibrium expression. You know, notice again, this Kf value is humongous. So it really is essentially like going to completion. Now, my gut feeling is probably most of you, hopefully, started setting up an ice table, yes?
Yeah.
Did you do this? Did you start with these initial values?
Yes.
Now, here's the problem I'm going to mention to you. You know, and tell me, this is probably how you did it, that, okay, so this is going to lose x, and this is going to lose 4x, right, 4x. This is going to gain x, and so you can plug all these things in and plug them then into your equilibrium expression. But what's the problem when you go to solve that?
It's too big. It's huge.
X is huge. Did you try to solve? What happened on your calculator?
My calculator remembered it to 0.2.
Yeah, because x is extremely, when you do this, x is so incredibly small that, yeah, many times your calculator is just going to say it's 0.2. Well, it's not. Your calculator's not entirely off base, because if you think about it, this K value is so big, it really is like, it's almost all going to react. We really are going to be left with hardly anything here. And when you put that in your calculator in an instance like this, you know, your calculator doesn't behave and give you what you want from it, more than likely. So in a case like this, it's far better to run it to completion to start with. And so what I mean is, essentially, this is all going to react. I realize in the end we're going to end up with a teeny tiny bit of it left. But with a K value that big, it's really like it's all going to disappear. That's what your calculator is really trying to tell you. It's all going. And then I'm going to lose 4 times that, so I'm going to lose 0.8. And I'm going to gain 0.2. And so in the end, I end up with this. Well, we can't really end up with 0. That's not our answer here. But it gives us a kind of a closer, we're really going to end up around 0.4 of this and 0.2 of this. And there's going to be a teeny tiny little bit left. So let's use these numbers here. And now let's work the equilibrium based on that. And it'll make it a lot easier, something that your calculator can deal with. So make a new ice table. And in making a new ice table, because essentially this is going to break apart again a little bit and reform it. Now, I didn't write this formula in terms of breaking apart. I just left it as a K sub F. But if you would like to write this as breaking apart because that's what makes sense to you, I'm totally fine with that. Because that is what's going to happen. We have this and this. It's going to break apart. what K value would you use if you choose to go this route?
Inverse of
The inverse. So here, if you do that, that way you do the inverse of the K sub f. But I'm showing it to you just using the K sub f. I am just going ahead and plugging in 0 here. And I'm going to lose some and gain some and go through it. And I can plug that into my original equilibrium expression from before. And then I 5%ed it. Because that x is, we already established that x is so small your calculator couldn't deal with it, so it almost certainly is less than 5% of 0.2. And so I 5%ed it. When you do that, you get x is equal to 1.6 times 10 to the minus 13, which I can guarantee you is less than 5% of these things. It's a really teeny tiny number. And so that is your copper ion concentration. So why did your calculator want to assume that it was, you know, losing all of it? Because, yeah, this is like 0.00, I don't know, 12 zeros, 1 6. It's a really tiny number. Or if we wanted to figure out how much of, you know, what's the ratio of complexed to uncomplexed, you know, take your 0.2 divided by 1.6 times 10 to the minus 13. You've got a really big ratio of complex to uncomplexed. So I want to just try to show you a little twist that sometimes occurs when we deal with K values that are so incredibly big that it's essentially like going to completion. Okay? All right, the rest of the time is yours, you guys. If you want to check your answers to the one worksheet from yesterday, they're right here. If you need to check any old answers from the reactions packet, they're over there. There's some blues on the board for you to work on. So if you got questions, just let me know.